Hey everyone, and welcome to another deep dive. Get ready, because today we're going to be exploring something truly mind-blowing. Quark soup. Now, it's not something you'll find on a restaurant menu, but it's a recipe that cooked up the entire universe.
It's true, and the amazing thing is that this soup, in a way, is still a part of you right now.
Okay, now I'm really intrigued. But before we get to how I'm connected to this cosmic soup, can we rewind a bit? Like, what exactly was it?
Imagine the universe 13.8 billion years ago, just a fraction of a second after the Big Bang.
So no galaxies, no stars.
None of that. Instead, picture an incredibly hot and dense fog. It was like a cosmic pressure cooker. But instead of vegetables, it's packed with the universe's tiniest building blocks, quarks and gluons.
So instead of a delicious stew, we have a chaotic sea of particles.
Exactly.
Can you break down what those particles are for us? What are quarks and gluons?
Think of quarks as the smallest Lego bricks imaginable. They're the pieces that make up protons and neutrons, which make up atoms.
Okay, I'm following so far.
And the gluons, well, they're the super glue that holds those quarks together.
So this soup was basically a jumbled mess of these tiny ingredients just bouncing around at crazy high speed.
It was pure chaos.
But how does any of this connect to us here today? You mentioned that I'm carrying a piece of this soup.
You, me, everything around us.
Yeah.
It all came from this quark soup. As the universe expanded and cooled, those quarks started to group together, forming the first protons and neutrons, and those eventually formed the first atoms.
Hold on. You're saying the atoms in my body were literally created from this primordial soup? That's wild.
It is. It's like the universe's ultimate recycling program.
Okay, so this soup had all the ingredients for, well, everything. But how hot are we talking here? I mean, my soup simmers on the stove. This stuff sounds more like a cosmic explosion.
You're not wrong to think of it as an explosion. The quark soup was a scorching 4 trillion degrees Celsius. That's 250,000 times hotter than the core of our sun.
250,000 times. Wow. Okay, that definitely puts things into perspective. So this wasn't just any ordinary soup. What if it happened again? Like, could quark soup just appear somewhere today?
It's a fascinating question. And scientists are actually trying to recreate tiny bits of this soup using machines called particle colliders. They smash particles together at nearly the speed of light, creating similar conditions to the early universe.
So we're essentially trying to recreate the Big Bang in a lab.
In a way, yes.
Doesn't that seem a little risky?
It is a calculated risk. The amounts of quark soup they create are incredibly small and contained. But it's true, the energy involved is immense. If a large amount of quark soup were to suddenly appear outside of a lab, it would be, well, catastrophic. We're talking about the potential to vaporize everything in a large radius.
Okay, that's slightly terrifying, but also really cool. So back to this cosmic chain reaction you were talking about. What if there was no quark soup in the first place? Would we even be here?
That's a great question. No soup. No particles, no atoms, no stars. Just an empty eternal darkness. It really shows you just how crucial that first fraction of a second was for the entire universe.
It's almost impossible to imagine a universe without, well, anything in it. I'm kind of stuck on the 4 trillion degrees thing, though. How can anything even exist at that temperature?
That's where things get really interesting. At those extreme temperatures, matter as we know it simply can't exist. Atoms break down, electrons are stripped from their nuclei, and even protons and neutrons melt away into their constituent quarks.
So it wasn't just hot, it was so hot that it basically broke down reality as we know it. What happened next? How do we go from this chaotic sea of quarks and gluons to the structured universe we see today?
Think of it as a massive cosmic cool down. As the universe expanded, the temperature dropped. And as it cooled, those free-floating quarks and gluons lost energy. They started to stick together.
Like a cosmic dance floor slowly emptying as the music stops?
Exactly. And as those quarks paired up, they formed protons and neutrons, which became the building blocks of atoms.
So the familiar stuff, the stuff that makes up us and everything we see, that all came from this cooling process.
It's true.
It's amazing to think that, in a very real sense, we're all made from the remnants of this incredibly hot, dense, and ancient soup.
We are.
And I'm guessing there's more to the story. This is just the beginning, right? I mean, what other mind-blowing details are hiding in this cosmic recipe?
Oh, there's so much more to explore. Did you know that there isn't just one type of quark? There are actually 6 different flavors of quarks, each with its own unique properties.
Wait, 6 flavors. So quarks are like ice cream now. Okay, now I'm really hooked. Tell me more about these flavors. 6 flavors of quarks. I am definitely intrigued. What are these flavors and how do they fit into this whole soup analogy?
Well, the names themselves are pretty quirky. You've got up, down, charm, strange, top and bottom.
It sounds more like a list of personality types than fundamental particles.
It does, doesn't it?
Mm.
But they describe the different properties of these tiny particles.
So there's actual science behind the whimsical names?
Oh, absolutely. The names help scientists distinguish the quarks based on things like their mass, electric charge, and how they interact with the forces of the universe.
Right.
Like the up and down quarks, they're the most common, and they're the ones that make up protons and neutrons.
Okay, got it.
The other flavors are a bit more exotic, showing up in high-energy environments like those created in particle colliders.
So the up and down quarks are like the basic ingredients of our soup, and the others are like spices that add a little something extra.
I like that analogy.
Okay, good.
And speaking of extra, let's talk about one of those spices, the strange quark.
Oh, this sounds intriguing.
Its discovery back in the 1940s really shook things up in physics because it lived far longer than anyone expected. It was so bizarre they called it strange, and, well, the name stuck.
So even the names of these particles have a story behind them.
They do.
It really highlights how this quark soup has been a gateway to incredible discoveries.
It has. And those discoveries continue. We talked about the incredible heat of the soup, but equally mind-blowing is how short-lived it was. We're talking less than a microsecond. A millionth of a second.
A millionth of a second? That's such a tiny amount of time. How can something that fleeting have such a lasting impact on the universe?
It really highlights just how dynamic and rapidly changing the early universe was. In that fraction of a second, the universe underwent a huge transformation. It shifted from pure energy into the building blocks of matter. And thanks to the cooling process, those building blocks eventually led to everything we see around us.
It really makes you think about how even the smallest moments can shape the grand scheme of things. We often think of the Big Bang as this big explosive event, but the moments that followed, like the quark soup phase, were just as important in creating the universe as we know it.
Exactly. And speaking of shaping the universe, remember those gluons?
The glue that holds the quarks together?
Yes, they are. But they're also responsible for one of the fundamental forces of nature, the strong force.
Right, the strong force. Can you remind me of what it does again?
It's the force that holds the nucleus of an atom together. You know, those protons and neutrons at the center. The strong force overcomes the natural repulsion between those positively charged protons, keeping them bound together in the nucleus.
So without it, atoms just wouldn't exist.
It wouldn't.
So gluons, these tiny particles from the quark soup, are the reason why matter can exist in a stable form.
They are. And studying quark-gluon plasma, that primordial soup, is helping scientists understand the strong force even better.
I can see how that would be valuable.
This research has implications for everything from nuclear physics to our understanding of the Big Bang itself.
It's fascinating how something as seemingly simple as a soup of particles can give us such profound insights into the forces that govern the universe. But let's go back to that soup analogy for a second. If the universe's first soup created everything, could there be other, cosmic dishes out there that we haven't discovered yet?
It's a question a lot of scientists are thinking about. As we delve deeper into the universe's origins and the laws of physics, who knows what we might find. There could be other states of matter, new forms of energy, other ingredients that lead to entirely new recipes for creating structures in the universe.
So there could be a whole cosmic cookbook out there waiting to be discovered.
Maybe.
That's both incredibly exciting and a little intimidating, isn't it? I mean, what if we stumble upon a recipe that we don't understand, or worse, one that we can't control?
That's the nature of scientific exploration. There's always a level of risk, but the potential rewards can be enormous. By understanding the fundamental building blocks of the universe, we might unlock new technologies, gain a deeper understanding of our place in the cosmos, even uncover new ways to harness the power of nature.
It's true. It reminds us that science isn't just about facts and figures. It's about pushing boundaries, exploring the unknown, and always being open to the unexpected.
Exactly. And as we continue to unravel the mysteries of the universe, who knows what incredible discoveries are waiting for us? The universe might be even stranger, more wonderful, and more delicious than we can imagine.
It's really amazing to think that something as, basic as a soup of particles could hold the key to understanding the universe.
It really highlights how everything is connected. From the smallest particles to the biggest structures in the cosmos, it all goes back to those basic ingredients and the forces that control how they interact.
We've talked about a lot today: the extreme heat, the incredibly short lifespan, those exotic quark flavors, and how gluons shape the universe as we know it. Is there anything else about this quark soup that really fascinates scientists?
One of the most interesting areas of research is trying to understand how we went from that quark soup to the first atoms. It's like piecing together a really complex puzzle. Figuring out how those quarks and gluons froze out into the protons and neutrons that make up atoms.
So scientists are basically trying to capture that moment when the universe was a baby and the building blocks of matter first appeared.
Exactly. By studying this transition, they're hoping to get a better understanding of the forces at play, especially that strong force we talked about earlier. It's like trying to figure out the rules of a cosmic game. How did those forces shape the universe from a sea of particles into the world we see today?
It's incredible to think that we can recreate those early universe conditions, even if it's just for a tiny moment here on Earth. What have those experiments shown us so far?
One of the big discoveries is that quark soup, or quark-gluon plasma, acts less like a gas and more like a liquid.
Oh, really?
It flows with almost no viscosity, which means there's very little friction inside it. Imagine a liquid so smooth it flows with almost no resistance at all.
Wow, that's pretty mind-boggling. So this primordial soup was incredibly hot, dense, and smooth. It's hard to wrap my head around that.
It definitely challenges our everyday understanding of how things work, but it gives us valuable clues about the early universe and the forces that shaped it. It shows us that the universe is full of surprises, and the more we learn, the more we realize how much we still don't know.
That makes sense. Are there any big questions about quark soup that are still unanswered?
Of course. One of the most fundamental questions is, what came before the quark soup? If this soup was the first form of matter, what existed before it? Was it pure energy? Was it something completely different? These questions push the limits of what we understand about physics. We have to consider possibilities that we might not even be able to imagine yet.
It's a good reminder that science is all about the journey. Every answer brings up new questions, taking us deeper and deeper into the mysteries of the universe.
Exactly. And that's what makes it so exciting. By learning about quark soup, we're not just learning about the very beginning of the universe, we're gaining insights into the laws of nature that govern everything, from tiny particles to massive cosmic structures.
This has been such a fascinating deep dive into the world of quark soup. We've explored its beginnings, its properties, its importance, and the mysteries it still holds. Any final thoughts for our listeners before we wrap things up?
I think the biggest takeaway is this. The universe is much stranger, more wonderful, and more interconnected than we often realize. Next time you look up at the stars, think about the atoms that make up your body. Remember that those atoms, and you, are part of a cosmic story that started with a bang in a bowl of the most amazing soup imaginable.
That's a beautiful way to put it. And to everyone listening, keep exploring, keep asking questions, and never lose that sense of wonder. The universe is a vast and mysterious place, and there's always something new to discover. Until next time, keep on diving deep into the unknown.